So I think it's time. So shall we begin? So
yes.
So we are very happy to have Professor Matti Lassas from University of Helsinki, Finland, and so he's going to give a set of lectures, 2 lectures on inverse problems for nonlinear partial differential equations and how nonlinearity makes imaging easier. So over to you, Professor Lassas.
And thank you very much. I would like very much to thank Venki for invitation. I really hope that the next time when you organize a physical workshop, I could visit you. But also this workshop seems to work very, very well, and so thank you for organizing that. So I changed slightly my title. I'm concentrating on this topic that how nonlinearity makes imaging easier. And so in my talk, I will start explaining first that why we do this study of nonlinear imaging. What is the motivation? Then I will explain basic tools, how we use nonlinearity, how we use geometry in study of inverse problems for waves, and how we use point sources. And last part of this mini course will be this kind of what part. I tell what's going on research just presently. Okay, so let's consider first the motivation. For instance, in nonlinear microscopy, that is very recent tool, one uses nonlinearity as a positive effect. And for here is an example where the nonlinear effect has been enhanced, so that this picture C1 is the usual microscopy picture. Then one has introduced small, strongly scattering particles, these kind of nanoparticles, close to the medium, which boosts up locally the signal so that nonlinear effects become visible and the image quality gets really much improved. And the point is that so physicists use nonlinearity to produce strong signals and also to get complementary information, because usually the coefficients of the nonlinear terms in the equations, they give very different information than the coefficients corresponding to the linear effect. Also, there is very interesting medical tools based on nonlinearity. For instance, the quantitative elastography, where you use elastic waves to measure physical structures, and this is used already in practice. So in the quantitative elastography, the idea is that you have some medium where you send an ultrasound wave. The ultrasound waves are actually mathematically they are elastic waves with p polarization. One focuses these waves, and they produce this kind of the focused wave produces new type of waves. This probably is also related to nonlinear process. And the focused pressure waves, they produce a shear wave that starts to propagate, and the shear waves are slower than p waves. And then one can use again pressure waves or ultrasound to measure how these shear waves move. Alternatively, people use also magnetic resonance imaging, but you can use also ultrasound waves. Usually physicists think that these are 2 different phenomena, that they are shear waves and ultrasound waves, but in reality they are just 2 different polarizations of elastic waves. And when you are measuring waves with other waves, then you are using actually nonlinearity of elastic equations. And this type of inverse problems have been recently studied by De Hoop, Ullman, and Wang. So this tells that this kind of nonlinear imaging works in practice. Let's look at these things then purely from mathematical point of view. What would be good motivations to study nonlinear equations? First is that this area is very rapidly progressing. In several recent results that are in the field, the nonlinearity is to consider now as an effect that aids solving the problem, not as a difficult perturbation term that one wants to cancel in estimates. So it is really a positive effect that you can use. And using this way of thinking that nonlinearity is useful, you can solve inverse problems for nonlinear equations for which the corresponding problem for the linear equation is still unsolved, in particular for equations with time-dependent coefficients. Then from mathematical point of view also, actually many physical models are nonlinear equations, and the linear equations that we often use are actually approximations of these nonlinear models. And finally, there are interesting purely mathematical research on nonlinear models, and also new effects like soliton waves. So these issues are the reasons why the nonlinear imaging is important in practice, and also the mathematics is interesting. So let me now next go to this how part of the talk, what type of tools we use to do this. And actually, if you have any questions on notations or concepts, please feel free to interrupt me, and we can somehow answer the questions. But let me first consider the question how we could use, what are the tools that we use, what tools we can use to study nonlinear equations and inverse problems for this. Our final goal will be actually consider this type of quite complicated interaction of waves, but let's start from simpler problems. Let me consider in the Euclidean flat space when wave speed is 1, the wave equation that is here with some nonlinear perturbation. So we have an unknown function q that is multiplied with nonlinear term u to power 3. And also in this part of the talk, we consider things in plane. So the dimension of the space is 2. So we consider this nonlinear wave equation. Now the wave speed is known and equal to 1. And the no unknown terms are in the coefficient of the nonlinear term. And then we consider Dirichlet boundary values for this problem. So we have a domain in R2. And on the boundary, we put the boundary condition. This f here can be considered as a source that produces the wave. And that's why I often denote it with the superindex uf. And we also consider the case when waves vanishes at time t is equal to 0. Then the boundary measurements are modeled by the Dirichlet map that maps this Dirichlet boundary value f to the normal derivative of the wave, that is the Neumann boundary value. So we map the Dirichlet data of the solution to boundary, to the Neumann data on the boundary. And because the equation is nonlinear, also this Dirichlet Neumann map in this setting is nonlinear. And the inverse problem is that we want to determine this function q of x. So we don't know what the equation is. We just know that when we put some boundary value, it sends a wave. The wave exists, but we don't know what it is, and we record that on the boundary. Or we actually record the normal derivative of the wave on boundary. And we consider this inverse problem. So let's consider linearization of waves. Later we are going to consider higher order linearization, and that's why I use different epsilon parameters. So I have a small parameter epsilon that I denote by epsilon 1. I consider a source or boundary, Dirichlet boundary value f epsilon 1, that is epsilon 1 times a given function f. And I denote by u epsilon 1 the solution of this nonlinear wave equation when Dirichlet boundary value is this small parameter epsilon 1 times a known source. So let's consider first what happens when epsilon is 0. So then the initial data is 0, boundary value is 0, so the solution of this equation is identically 0. And then we consider what happens when we change epsilon a little bit. We compute the derivative of the solution with respect to this epsilon parameter. This we denote by u1. How we do that? We just take this equation and differentiate all terms here with respect to epsilon. And the epsilon derivative commutes with all other differentiation. So this term here, when it's differentiated, it gives us the linear wave operator that is here. Then we compute the derivative of this term with respect to epsilon. When epsilon 1 is 0, then this term vanishes. So we compute the derivative of u to power 3 at 0. This gives us value 0. So the nonlinearity vanishes. And we are left with a linear wave equation for u1 with the boundary value f1. Let's consider now this linear wave equation. What type of waves we would like to consider? We are going to use so-called plane waves. So they are visualized in this picture. We have this kind of bump that is moving. When here is time t is equal to say 1. Here is t is time t is equal to 2. Sorry, now I said wrongly. Here is t is 1. Here is t is 2. So the wave is propagating to this direction. How we do this? We take a test function or this kind of bound function, a smooth, compactly supported function. And in 3-dimensional, sorry, this should be 2-dimensional. Now this 3 should be 2. So we are in 2-dimensional space. We take a vector that has length 1. And then we consider a wave, that is this function, bump function phi, evaluated at just some constant plus t minus theta dot x. This is constant on planes. So this S parameter here tells what is the delay where the wave is at time t is equal to 0. This wave propagates to direction theta. And if I just take this type of plane wave in the whole R2, I compute its boundary value on the boundary. Then I see that this pair U1 and F1, they satisfy this linear wave equation. So I can think that, okay, I have function F1 that looks like this. I know what it is. And it produces a plane wave that propagates to direction theta. So this is the corresponding one-dimensional picture. Let's use this type of linearized waves. And we are going to use several of those. But to consider nonlinearity, we are going to use higher order linearization. We use third order linearization of the problem. So because of that, I introduced 3 epsilon parameters. So this epsilon 1, epsilon 2, epsilon 3, they are all small real numbers. And I take some boundary values fj's, and then I take a linear combination of these fj's by multiplying them with these small epsilon parameters and summing those together. Then I consider u epsilon vector, that is solution of this nonlinear wave equation. When I use this little bit more complicated boundary value f, u epsilon vector, that is given here. And let's now differentiate this. If you differentiate it once with respect to say epsilon 1, then we are obtain like here we get a linear wave equation because the derivative of this nonlinear term here, it vanished. Now we have third order nonlinearity, and then we differentiate it 3 times. Once with respect to each epsilon parameter, we differentiate it first with respect to epsilon 3, then with respect to epsilon 2, then with respect to epsilon 1. So actually you can think these epsilons as the same variables. We differentiate this u to power 3 times. Then it's not anymore vanishing. So when we differentiate this with respect to these variables, we will get this type of term that appears here. And this is now considered as an interaction of waves. We have 3 linearized waves, u1, u2, u3. They produce a source that we call artificial source. And this appears for the equation for this third order derivative. So this is what we are going to consider. And this is the positive effect of nonlinearity that we can use to aid in image. Let's now consider different type of linearized waves, u1, u2, u3, so that we can apply this formula. For that, then recall that we use this bump function. Now I do scaling. I scale the bump function by parameter h. So I divide time with h and multiply this obtained function 1 over h. So this is these are often called modifiers, this type of functions. So let's go to this picture here when we had this bound function that was propagating. Now when we put this parameter h there, that squeezes time, then this pulse will have a shorter time, and we multiply it by 1 over h, so the height of the bump gets larger. So it starts to be shorter and shorter pulse that is higher and higher. Sorry. And then these modified bump functions, they will actually approximate Dirac's delta distribution. So let's look this. I'm sorry if I still have this misprint here. Here should be r to the power 2. So I consider some unit vector theta j. I have this kind of delay parameters sj. And then I consider plane waves that are these very short pulses with delays sj that propagate to direction theta j. So these are like plane waves that propagate in plane, and then they start to be shorter and shorter pulses that get higher and higher. And they are produced by these boundary values that I just have obtained by taking this wave and I evaluate it on the boundary. So these functions fj with index h, they produce these plane waves. And now is the important point. When h goes to 0, then these plane waves, they go to a delta wave. Here we have a delta distribution. I was told that the audience contain here both like some undergraduate students to senior researchers. So I recall some of these concepts. So delta distribution is recorded here. It is like a measure or generalized function. You can think that as a function as physicist, so that it is a function when we integrate this function and some smooth complex supported function with this, then this here is a measure that has all mass at the place t is equal to s. So this integration gives phi of s. So anyway, these bound functions, when h goes to 0, the pulses get shorter and shorter, and this becomes infinitely short and infinitely high pulse. Mathematically, that is a delta distribution. So we can consider delta waves that are propagated. Let's choose the directions. Actually, I have some pictures, but I choose the these vectors, theta j's, so that I can make easily computations. I take first this theta 1, that is the unit vector to x direction, then unit vector to y direction, and then unit vector to minus y direction. I recall that we use this type of boundary values, and those produce us these three plane waves. So because of the sign change here, the sign is changed. So this propagates to let's see, to positive x direction. This propagates to positive x2 direction, and this propagates to negative x2 direction. And when h goes to 0, these go to delta distributions. So we have 3 delta waves that propagate to different directions. Let me show a schematic picture of this. So now I took this from Reed and Raut's paper, and there the plane waves are slightly differently directed. So we have a wave that is supported on a line at given time t. So I have a delta wave or a plane wave that propagates to this direction. Yeah, I have other plane wave that propagates to this direction, and a third plane wave that propagates to this direction. So that this here in this formulation, the picture, these theta vectors are slightly different than in these formulas. Next, we want to understand what happens when all these delta waves collide. They will produce something that I will explain soon. But we have now 3 plane waves that are propagating in plane, and then they will all collide. Let's try to understand why they produce a new wave. This is our goal. And let us somehow recall our setting. So I actually denote by box or square the wave operator. We have a solutions of these nonlinear equations that depend on 3 epsilon parameters. And I recall when epsilon is 0, the wave is 0. Then I differentiate respect to 1 parameter. I get a linearized wave that satisfies the linear wave equation. And when I differentiate 3 times, I get for the third order derivative W3, I get the wave equation that the wave operator of W3 is equal to S, where S is a function that is product of these linearized waves times Q. We call this S here an artificial source. Where this comes from? This comes from the idea that in this equation we don't have any physical sources. But in this equation, it appears that we have a source there. So this is not really a physical source in the sense that we don't put it. But the nonlinear term starts to act as a source. And we call this an artificial source produced by the 3 interaction of the waves. And this is what we are going to use. And let's look what happens now when these 3 waves are plane waves. So this is a picture in space-time now. So the space is the horizontal direction, and the vertical direction is time. In space-time, these plane waves, they are actually planes. And then they intersect in different ways. And what is interesting that when 3 planes, this 3-dimensional space, when they intersect at a single point. And this point will be very interesting point because it will produce as an artificial point source. So the intersection of 3 planes is 1 point in space-time. Let's look how this appears in computations. We use these kind of bump waves that propagate to certain directions. And when we compute the artificial source for these three smooth plane waves, then we get product of these 3 functions multiplied by Q and some constant. And let now H go to 0, so that the pulse length goes to 0. Then this interaction source, this SH, it converges to S. S is the product. We have this -6 times Q, that is here. And then we have product of 3 delta distributions, 3 delta waves. And in next slide, I will see that actually this product of these 3 delta functions, they can be written in much simpler way. That it is actually delta distribution in x1 variable, delta distribution in x2 variable, delta distribution in t variable. So they correspond that in this picture. I have delta distribution supported on planes. I multiply them together. I get the delta distribution supported at the point. And then I can compute what is the point where this delta distribution is supported. And it is a simple computation of just linear algebra. One more important thing is that I had this unknown function Q that I want to find out. I multiply that with these delta distributions, or here with these 3 delta distributions. This delta distribution is supported in 1 point, so only the value that Q has at this point, where the delta distribution is supported, that is important. So this unknown function Q is changed to a constant. Here's the computation what I did. So let's consider these computations when S1 is 0, S2 is 0, S3 is 0. So then it is here. I have these 3 delta distributions, and I multiply those with some test function psi. Then I just change the coordinates. I introduce new coordinates, that here is y1, here is y2, here is y3. I change the coordinates, I evaluate this psi at the changed coordinates, and I multiply this integral with the determinant of change of the coordinates. This determinant gives value 2. So of course it should be 1/2. Okay, sorry. Yes, and then I have delta distribution multiplying by this function. I just evaluate this psi at a minus 1 at 0, and this gives me psi. This explains why this product of these delta distributions is the same as this product of 3 delta distributions. Okay, so let's see what we have obtained. We had that the nonlinear interaction of 3 waves. So in this derivative here, I call it the interaction of 3 waves. It produces a wave that is solution of the wave equation with the artificial source. This artificial source S, we computed it. It is this constant times delta distribution. So let's see what this now means from the point of view of boundary measurements. We recall that we assume that we are given the nonlinear Dirichlet-Neumann map that maps the boundary value f of the function u to the Neumann boundary value, the normal derivative of the solution of this equation. Let's see what we can do. So we can put inside this Neumann, inside this Dirichlet-Neumann map, we can put our special source, that is linear combination of 3 sources on boundary. Then we differentiate this 3 times. So if lambda is given to us, we can compute what this is. Then we can take also limit when this pulse length h goes to 0. So this Dirichlet-Neumann map inside here, this is the Neumann derivative of the solution of this equation when this f is given by this linear combination of 3 sources. Let's now change the order of differentiation. I may move all these derivatives inside the normal derivative, and then I let also h go to 0. I am left to the normal derivative of 3rd order interaction wave, and this 3rd order interaction wave, which is written here, it's the solution of the wave equation with source S, where S is a constant times delta distribution. So let's recall from theory of partial differential equations. Let's use theory of partial differential equations to say that what is the solution of the wave equation when solution is constant times delta distribution. That is written, record here. So when we have a solution that is delta distribution, so we have delta distribution that is supported at point x at time t. The solution of this linear wave equation with point source is called Green's function. And when you know the domain omega, you can compute this explicitly, or at least numerically you can compute it, and you also know it's well-defined object. Then this quantity that the quantity that the nonlinear Dirichlet-Neumann map gives to us, normal derivative of the 3rd order interaction wave. This will be constant times q evaluated at this point where the delta distribution is supported times normal derivative of the Green's function. But this normal derivative of the Green's function has nothing to do with q. It's just a solution of a linear problem in domain omega. So we know what it is. When we record this, if we know this here, we can find out what this q at point x star t star is. So I recall, we know what is the Dirichlet-Neumann map. So we can take and compute this formula by knowing the lambda map. this map gives us this normal derivative of W3, and the normal derivative of W3 is a constant times the function that we want to find times something known. So that's how we can reconstruct the unknown potential. So what happened here? We had three plane waves that are moving, then they collide. When they collide, the nonlinear interaction produces a point source at this collision point. That is a delta distribution times the coefficient Q of the nonlinear term. And then this delta distribution produces a spherical wave that propagates to different directions. And this is what we measure at boundary. And the magnitude of the source is the same as the amplitude of the wave that is produced. And that is just value of the unknown function Q at this point of where the waves collide. So because we can engineer different delays in these plane waves, we can decide what is the place where all these three waves collide. So we can measure what is the value of Q at different points. And this is how we solve the inverse problem. Are there any questions by chance at this stage on this material, on these principles? Of course, I have put under wrap many difficulties, but anyway, so these are the main ideas. Okay, let's move then forward. So now the first is how to use nonlinearity. This part we considered Euclidean space. The wave speed was constant. Actually, when wave speed is not constant, we are going to use geometry to study the inverse problem. So let's move to this part. And for this end, I actually consider what happens for the inverse problem for linear wave equation and how geometry appears here. And this kind of, at least in my own mind, the picture that I always have is something like this, that we can do medical imaging or we can do seismic imaging. That we have here, like this is the typical configuration. We have sources close to the boundary. These are so-called air guns. That there's a huge container that is full of air. When opens it rapidly, water rushes in and produces a strong sound wave that is propagated. And then there are microphones where you measure these reflected waves. So how to model this? Let's now consider domain that I now denote by M because I want to consider it as a manifold. But at this stage, let's consider a domain M in Rn, open domain that has a smooth boundary, and nu is the normal vector. Let's consider now the linear wave equation with varying wave speed. So the c of x here is the wave speed, and this is assumed to be unknown. And again, u with index f here, this is the solution of this problem with the Neumann. Now it is with the Neumann boundary value, normal derivative of u is equal to f. And this f here physically can be considered as a boundary source. So it's really like this source produced by these air guns. And we assume that we are given now the Neumann to Dirichlet map that maps this known boundary value, that is now the Neumann data, to Dirichlet boundary value of the wave. So this is one of the basic examples. We have here wave speed c of x. But this is not very good model because often medium is not isotropic, but it is anisotropic. And anisotropic means that we just take the same wave equation, but we replace the wave speed with a matrix. So we have here the gradient multiplied by a matrix, and then its divergence. And often one adds here a function kappa, but we will assume that this kappa function is 1. So we have a matrix-valued wave speed, which says that the speed of waves depend what is the direction where the waves are propagated. And we could ask, could we reconstruct this matrix G when we are given the Neumann to Dirichlet map. And now in this setting, the Neumann to Dirichlet map is linear operator, and this equation also is linear. Okay, how geometry comes into the play. We can consider this domain M as a Riemannian manifold with the non-Euclidean metric, because the non-Euclidean metric that we consider now is the travel time. So we say that instead of saying how many meters there is from here, for instance, to Bangalore, I ask how long it takes to travel by some means from here to Bangalore. So the travel time is considered now as a metric. And this metric has a length element ds that is given by this metric, this tensor, this matrix G. Actually, I use this convention that is typical in differential geometry, that when I have lower indices, that is the inverse of the matrix when I have the upper indices. For instance, if you have isotropic wave speed, then the travel time metric is a metric where the length element squared is distance squared divided by speed squared. So it's very physical. So that is that this metric tensor, we call it tensor, GJK, is scalar wave speed to power -2 times identity matrix. And then we say that the distance of 2 points, the distance, sometimes I will write it as a distance or just d of point x and y, is the travel time of waves from point x to y. And we are going to consider this domain in Rn as a manifold. So what manifold is? Manifold is a collection of local charts. For instance, the spherical surface can be considered as a manifold. There is a collection of charts. So here is this abstract manifold, but it can be just a domain in Rn. And then it has different open sets where we have local coordinates. We can map this area to here with one set of coordinates. So this is in Euclidean space. We have some other coordinate chart that we map to Euclidean space. And the manifold is the collection of these charts. Like here, it's just the name comes from the map chart. And then we have a rule how we go from one map to another. When the charts are here, when the neighborhoods here are overlapping, there's a rule how to go from one chart to other chart. Okay, so but with this generalization, we can take a manifold that is just abstract topological space that can be covered by local coordinate charts. We can define in all charts Riemannian metric that is actually just a matrix, valid wave speed. And then we define the Laplace operator with this formula. So this metric G is now a matrix. G with upper indices is the inverse matrix. Here we use the determinant of this matrix. And this is how we write the Laplace operator on Riemannian manifold. So for instance, if you would have a domain in open set M in Rn, and we have there matrix valid wave speed that gives us function GJK, we can consider it as a manifold with only one chart. And in particular, if we are in two-dimensional case and we have this type of isotropic metric, then this Laplace operator with respect to the metric is just this operator that appears in the wave equation. So this is a generalization of the waves on abstract manifolds. And we say that the wave equation on a manifold is this equation when we have replaced, for instance, this difference operator by the Laplacian of the manifold. And again, we can speak about the normal derivatives and define the Neumann to Dirichlet map that maps the Neumann data to Dirichlet map. And the inverse problem is that we assume that we are given the boundary data, that is the boundary of the manifold, and we are given this Neumann to Dirichlet map, only those, and we ask, can we determine a manifold that is isometric to the manifold where the wave equation takes place? One could ask, why on the earth we want to do this generalization? Let me explain that next. So now when we have an open domain in Rn, and we have a matrix valued wave speed, then there's the following observation which says that the inverse problem cannot be solved uniquely. Namely, we can take a diffeomorphism of the domain. Here is the domain. We do the diffeomorphism, so we just like deform it continuously. This can be also considered as change of coordinates in some sense. Then when we can take the metric, this metric value wave speed g1, and we can say that how it transforms in this diffeomorphism. So we have here metric g1, then we want to push it forward to metric in this diffeomorphism. And here is the rule. We just use the derivative matrix of the diffeomorphism, multiply it from two sides with this matrix g1, and evaluate it in correct place. What it then turns out? It turns out that if you define that G2 is obtained by this formula, so that G2 is the push forward of metric G1 in F, then the boundary measurements, the Neumann-Dirichlet maps with wave speed G1 or wave speed G2 are the same. So the boundary measurements cannot separate wave speed here or wave speed here. There are two different physical mediums that give the same boundary measurements. So one cannot solve the inverse problem. And in this case, we also say that this manifolds M with metric G1, manifold M with G2, they are isometric. And we say that this mapping diffeomorphism F is isometric between these two manifolds. Okay. To understand like this even in more practice, let me introduce a concept of geodesic. A geodesic is a curve that is locally length minimizing. So it just means that when I loop one curve here, I take two close by points, then the geodesic is the shortest curve between these 2 points. If the geodesic is very, very long, then it might be that for on long distances, the geodesic is not anymore distance minimizing, but locally in small neighborhoods, it's always length minimizing. And if we have a Riemannian metric tensor G with this length element, then there's a simple way to compute what are the geodesics. In differential geometry, it is shown that they satisfy this type of ordinary differential equation, where the coefficients, these gammas, so-called Christoffel symbols, can be just computed explicitly from the wave speed function G. So, and these are, for instance, in optics, geodesics are light rays along which light propagates. So let's now go to very practical imaging example. Let's consider just standard ultrasound. So here is a standard ultrasound picture. Here is an emitter that sends waves. And this picture actually here, this shows this actually shows reflection coefficient. Let's see. So let's think of it. This sense shows the some kind of reflectivity or wave speed. Actually, this shows some reflectivity, assuming that the sound waves would have traveled along straight lines. Now, when you change the sound speed inside body, this and the sound is actually propagating along geodesics that are curves, so that are called geodesics or rays in acoustics. So these black lines are how the waves are really propagating in physical space. But in this kind of imaging problems, like here, this image here, in this picture, the image is done as if the sound would propagate along straight lines. So basically, you would think that here, when you think a line, it says that wave has propagated some time and then reflected back. Physically, the wave has propagated along a curve, reflected back. But in this type of image, one shows the image on the computer screen, assuming that the waves would have traveled along straight lines. So what is the moral of this? So this really is not a physical picture, it's a picture in transformed coordinates. And those in geometry are called Riemann normal coordinates, and in ultrasound imaging, they are called ray coordinates. Also, never when you have ultrasound image, never plan an invasive treatment with needle or anything like that, only based off this picture, because this is the coordinates in this picture are not physical coordinates. This is picture in deformed coordinates. Okay, so how to solve the inverse problem in this setting when we could use this abstract language of manifolds? We have some signals, that is the Neumann to delay map. We use those signals to reconstruct a Riemannian manifold, an abstract manifold, that you could here are these two-dimensional manifold that is embedded to some higher dimensional space. And then you want to take this abstract manifold and you want to embed it to Euclidean plane. So you first use data to reconstruct the abstract Riemannian manifold, and then you construct an embedding of the abstract Riemannian manifold in R, like R2 in this picture. And we observe that there can be several different embeddings, like in this picture. There are like different physical wave speeds that gives the same measurements. This means that the abstract manifold that we reconstruct, that can be embedded in Euclidean space in different ways. Actually, this kind of considering this type of abstract manifold and embedding it to low dimensional space, this is very closely related to this manifold learning and the famous manifold testing conjecture that was solved by Pfefferman and Mitter and Naranayan. Naranayan is actually from Amber. So they are. This is also related to this kind of learning. Anyway, so what is this kind of plan that you reconstruct the abstract manifold, and then you construct an embedding, what it means in practice? So this is the basic result for linear wave equations. This was done by Berisha and Kurilev. That was applying Tatarov's unique continuous result. Let's assume that we have a domain in Rn, an open set, and we have two matrix-valued wave speed functions. And then we consider the geometric wave equation with this Laplace operator, and assume that the boundary measurements are the same. Then one can show that you can reconstruct the manifold structure uniquely, which means that if the boundary measurements coincide, then the manifold or this domain M with the metric G1 and the same domain with metric G2 are isometric. This means that there is a diffeomorphism that keeps the boundary the same, so that this wave speed functions G2 and G1 has this relationship. So you can reconstruct the wave speed up to change of coordinates. This sounds so that, okay, that's really bad because you cannot reconstruct that. But it actually says that if you reconstruct local charts, images in local charts like here, those coincide. But one can also apply this in different ways. If one restricts the form of the equation, that is some slightly different. For instance, if we assume that the wave speed, so we assume that the wave equation looks like this. So here we had this kappa function that we assume now that is 1. So if the wave equation that we study, the physical model that we studied looks like this, then this diffeomorphism SF has to satisfy a special additional condition that the determinant of the derivative is 1. That is, F has to be volume preserving. So this means that for these equations, you can reconstruct the wave speed up to volume preserving diffeomorphisms. Finally, if you make even more restrictions, you assume that the wave speed is scalar, then you have that this map F has to be the identity map. Sorry, here is some background noise. I come in a second. Sorry for the break. So, what this means that you can reconstruct from boundary measurements uniquely an abstract manifold structure. And then if you want to embed this manifold to Euclidean space to solve the physical inverse problem, and depending now of the form of the equation, you get less and you can get more or less freedom in the embeddings. And then for this type of wave equations, you can solve uniquely for this wave speed. So this was about the linear waves. So here are some like studies on linear waves, and I want to emphasize a few things that are related why we do nonlinear wave equation. So and I want to emphasize that originally the problem was solved by Bayesian and Kurileva and Tataru. And there are also recent nice numerical results by De Hoop, Kepri, and Oksanen. There are two difficulties. One is that this problem has very unstable solution. Just very recently, with Burago and Ivanov and Lu, we showed that this problem is log-log stable, so extremely bad stability. And other thing is that the main tool, the Tataru's unique continuation theorem, it fails. There are counterexamples when coefficients are not real analytic functions in time. So in practice, it means that if the coefficients are time depending, then you cannot use this type of methods to solve the problem. Okay, this is one thing why we consider the nonlinear inverse problems, that we can then solve the inverse problem in a wider class of operators. Finally, let me go to this question, how we can use point sources in imaging. This was very much crucial in this first part. Now we assume that we have point sources and we have a Riemannian metric, or we have a varying wave speed. Let me first give a motivation, like how this would look like. Let's assume that we have measurement domain, that is this blue set here. And then I have some unknown domain where I have sources that can go off and produce a wave. This is very typical. So let's happen what happens here in this setting. Let's assume now that some of this source goes off. So this becomes active. It produces a wave that propagates. And it goes through the domain where we do observations, and we see the wave there. Then we wait for a while, and that later some other source becomes active. And this produces a wave that we observe here in the measurement domain. And then we ask that from this type of observations, what we can say about this known unknown region here. That there are lots of point sources. This type of problem is actually encountered in seismic imaging, because after a large earthquake, there are lots of micro earthquakes, like very small earthquakes in the same area. So in this sense, you could image Earth by using these micro seismic events that appear after larger earthquakes. So let me recall how we consider the point sources. So like earlier, we use Green's functions. So the Green's functions are now waves. Here I again have in this example I have a constant wave speed, but we are going to change this. And we have a delta source that produces a wave. For instance, in Euclidean space, when we have a source at point 0 at time 0, this is how the wave, the Green's function, that is the wave produced by the point source, how it looks like. So it's a delta distribution evaluated at time t minus absolute value of x divided by absolute value of x. So it is like this is the picture in space-time. time is the vertical direction and horizontal direction is space. You have here a point source that produces a wave that propagates along the light cone. And if we somehow change the place where the point source is at point x star and it happens at time t star, then we just change the time and change the origin. So this is how the Green's functions look. Let us assume that we have some domain where there are lots of point sources that can go off at some time. And we say that when this point source goes off and produces a wave, then we ask, what is the time when we observe the wave at some boundary point z? So let this t function, t x star, t star, z be the first time when the wave produced by a point source is observed at this boundary point. What it is? It is the travel time from the source point to the boundary point, plus the time when the point source went off. And because these travel time distances appear here, we actually define the concept of boundary distance functions. And they are the following. Let x be a point of the manifold. Then the boundary distance function, Rx, is a continuous function on the boundary. Its values are Rx at point 0 is the distance from x to z. So it is the distance from this point here to boundary points. It's a travel time from this point x to point z. These boundary distance functions are continuous functions on the boundary. So we can define a map that maps points in the manifold M to continuous functions on the boundary. So that point x is mapped to the corresponding boundary distance functions. And we can define the set of all boundary distance functions. We would think that so actually, yes, so we can define the image of this mapping R. This is the set of all boundary distance functions. Let us assume now that we know that there are lots of point sources inside here, and they would go off at some times that we know. Then we had the following problem, that we have for all points x in the manifold M, or actually for dense set at least of those points, say dense set of points x, or maybe say all points. That's the same thing actually. We know the boundary value of the Green's function when we know that the time when the source became active was 0. This gives us the family of boundary distance functions. So we have the family of all functions in space of continuous functions on the boundary. And we ask, can we reconstruct the manifold when we know the boundary and we know the set of boundary distance functions? Here actually there may be a bit of confusion because the physical example that I considered was that this, like in this example here, the point sources went off, that they became active at some unknown, somehow random times. In this somehow setting, I assume that I know when the source becomes active. There are research also for this question that how we can consider the inverse problem when we don't know the times when the source becomes active. But now in this talk, I assume that we know that the source became active at time t star is 0, and then this first observation time here it coincides with the distance from x to z. And there are results which say that when we are given the boundary and the collection of all boundary distance functions, then we can uniquely determine the topological, the differentiable structure, and the metric on M up to an isometric. And I think that we will have soon break, but after the break, I will explain the proof that is relatively like elementary, fortunately, in the case when the manifold is simple. So this is what we are going to do after in the second hour. Are there any questions on the material this far, or any comments in general, please?
Yeah, so I have one question.
Yes.
Yeah, so the thing is that for creating this artificial point source, what you have mentioned in your first part, so it seems like there are 3 plane waves necessary.
Yes.
So are there?
Yes, let me go to the sorry, okay, please, yes, sorry.
Yeah. So are there results on when this means nonlinearity is square type or something, square type nonlinearity?
Yes. So actually, in this problem now, yes, that is excellent question. So here, to somehow give it the basic ideas, I used 3 things that were the key things. So first was that I like you noticed we had this third order nonlinearity, and we used the space that is 2-dimensional. So actually the omega times r plus this is 3-dimensional. So the dimension of the space-time is just the same as the nonlinearity. And the reason for this was that the picture here in the space-time, we have 3 planes that are intersecting, and then the intersection is a single point. So we were considering a case when we had a happy coincidence that this is the valid. And this can be relaxed, and I will actually speak a little bit about that in the next hour. But that was an excellent question. Did this answer to the question?
Yeah. And one thing is that when you will be considering this finite time cylinder, means I think you are considering infinite time cylinder. So for finite time cylinder, so you will be recovering these coefficients on this cone, on this diamond type shaped, or
yes, let's see.
So will you be needing these initial measurements or initial or final measurements, or for finite time cylinder?
Yeah, sorry, do you mean we were considering these inverse problems for the linear wave equation, or for the nonlinear?
For the nonlinear type, like box plus q u cube.
Yes.
So for that, so when you consider this finite time cylinder,
yes.
So your cylinder is t can vary up to say capital T. So do you need this final time measurements, or?
Yes, let's see. So here the time interval was infinite, but you can solve also. You can consider this problem also with the whole r plus is replaced by a finite time interval.
Okay.
But then you have like restrictions that what you can see, because if you have so we don't have we don't have any initial data that is considered 0. We don't measure anything at the final time.
Yeah.
So if here would be a finite time interval from 0 to t capital, then the way with anything that happens close to t is t capital, it cannot reach the boundary.
Yeah.
And that then it would be totally invisible to all our observations.
Yeah. So for finite thing, you will be needing those things, initial and final also. Both you should need those.
Let's see.
Yeah. Okay.
I think that then you would somehow need if you want to put here a final. So if you put a final time interval, either you get you can reconstruct Q in some subset that is such that this construction works and information can propagate to the boundary, or you can. Okay, I noticed also that actually in this setting that I now was explaining, also. So yes. Actually, I'm about to say we cannot solve the whole. We cannot reconstruct Q in the whole domain, because when time is close to t is equal to 0, then we cannot reconstruct Q in very small times in the middle of the domain, because no waves can approach. No wave can go from the boundary to interior in very early times. So yes. By the way, please, when you ask questions, it would be very nice if you also introduce yourself, because I don't know who is asking the question.
I'm Somen Senaputi.
Okay. Yes. Thank you for the question. Yes.
Thank you.
So, Matti, this is Venki. I also have a related question. So one thing is what about if you have like fractional nonlinearities, like instead of U cube, like, so here you have positive integer nonlinearities, right? But what about the case for fractional nonlinearities?
Yes, those has been studied for, let's see, for elliptic equations, those have been studied. This is actually like the top, this whole research of this on these nonlinear equations is there are not so many, but there are lots of open problems at this moment. I'm not sure if fractional nonlinearities has been studied for the wave equation at this moment. These kind of techniques probably work.
So this you're saying this type of techniques will probably work in the fractional case also?
So when you have a fractional power here, these techniques probably work. If you have a fractional differential operators, then I don't know anything about that, but it depends really a bit what type of fractionality you mean. Yeah.
Okay. I was only referring to, like, instead of U cube, let's say we have U power 1/3, something like that.
Yes. Let's see. Yes, so there are results when this function here is replaced by an analytic function. So when the nonlinearity is replaced by some analytic function. Let's see, like if you would have here to the power 1/3, then there might be some difficulties. So it is an interesting question. I think it is an open research problem.
I see. And the other question, thanks. And the other question is, if you have finite time cylinder, right? And then if you assume Q is independent of time, then are there, like, you can expect probably better results, no? You can actually solve it.
Yes. So let me go a little bit. With some little bit later in my talk. Yeah, so at this moment, so this what is this when you have finite time interval. This is some additional material that probably I cannot go through, but so that for instance, if one assumes now that like the diameter of the domain is known, and then one has two times, like when both times are larger than the diameter, and satisfy some conditions. Then if you assume that Q is supported on omega times some smaller time interval, the smaller time interval is used so that the waves can propagate from boundary everywhere to the domain, and actually that from any point on the boundary the waves can reach any point of the domain. And also so this is why T1 is larger than D. And then we assume that also that we have the potential is supported in times before T2, and small T2 satisfies this condition here. So this guarantees that all signals from the support of Q can reach the boundary. So there are this type of results, but then the domain where Q can be reconstructed are restricted.
Yeah, thanks. Yeah, any other questions? If not, thank you, Matti, and we'll see in approximately 50 minutes.
Yes, thank you very much.
50. Thank you. Okay.
Thank you.
All right.
Bye.